Welcome to the course on Numerical Linear Algebra and Application. Today we are going to learn the 44th lecture of this course. Before going to the contents of this course, let us quickly recall what we have done in the previous lecture. In the previous lecture, we have learned about the iterative procedures. The iterative procedures, Gauss-Jacobi method, Gauss-Seidel method, successive over relaxation method. We have seen that the convergence of these three methods, how fast they are for a particular application. Today we are going to have a numerical matrix eigenvalue problem. Numerical eigenvalue problem is a very important practical problem and arises in a variety of applications, especially in engineering, physical and chemical, statistical areas. Since the eigenvalues of a matrix A are the zeros of the characteristic polynomial determinant of A minus lambda I, one would naively think of computing the eigenvalues of A by finding its characteristic polynomial and then computing zeros by a standard root finding method. Unfortunately, eigencomputation via the characteristic polynomial is not a practical approach. A standard practical algorithm for finding the eigenvalues of a matrix is the QR method. What is this QR method? The QR method is decomposition of two matrices Q and R with a single shift or a double shift. We have seen several applications do not need knowledge of this spectrum. A few selected eigenvalues, usually a largest or smallest ones, are sufficient. A classical method based on implicit power of A, known as the power method, is very useful for this purpose. In this power method, what we do is we start with some initial vector, say x of 1, normally a 0 vector, and in the course of time we try to approximate x of 1, x of 2, so on and so forth, such that Ax is equal to lambda x. Eigenvalue problems arising in number of practical applications. The problem of finding eigenvalues and eigenvectors arises in wide variety of practical applications in science and engineering. The word eigenvalue and eigenvector are Greek words. As we have seen number of occasions, the mathematical models of many engineering problems are system of differential and difference equations. And the solution of these equations are often expressed in terms of eigenvalues and eigenvectors of the matrices of these systems. Further, many characteristic polynomials of engineering and physical systems which do arises, we do try to compute or determine by knowing the nature and location of these eigenvalues. We'll give a few representative examples over here. The first one is so-called stability problem for differential and integral equations. A homogeneous linear system, we write it as x dot of t is nothing but a times of x of t and x of 0 is equal to x naught, where the matrix A is a coefficient matrix and the form of that xt is nothing but d by dt of x1 of t, x2 of t, xn of t arises in wide physical engineering systems, which we can tell in terms of the theorem. The solution of this system is intimately related to the eigenvalues of the matrix A. This is the matrix A, Aij m over n. Many interesting and desirable properties of physical and engineering systems can be studied by knowing the nature and location of these eigenvalues of the matrix A, and one such property is the stability system. Now, before going to the stability system, an equilibrium solution of 1 is the vector xe such that Ax is equal to 0. A times of x of E is equal to 0. So, an equilibrium solution Xe is asymptotically stable if there exists a delta greater than 0 such that the norm of x of t minus x of E approaches to 0 as t approaches to infinity. Whenever norm of x naught minus x e less than or equal to delta positive. So, system 1 is asymptotically stable if the equilibrium solution Xc is equal to 0 is asymptotically stable. A system that is not asymptotically stable will be called as unstable system. So, for unstable system, we are not going to have an approximate solution to the best extent. Asymptotically stable guarantees that if the system is perturbed from the position of the equilibrium a little bit, then it will eventually return to that position after making small oscillations. So, what is the mathematical criteria for defining asymptotic stability? A necessary and sufficient condition for system 1 to be asymptotically stable is that the eigenvalues of the matrix A all have negative real parts. It is unstable if at least one eigenvalue has a positive real part. So, the proof would be very simple over here. We will sketch the proof in the case when A is diagonalizable. That is, in this case where there exists a non-singular matrix X such that X inverse Ax is equal to diagonal of D, which is lambda 1, lambda 2, lambda n, like this. Again, if lambda I is equal to alpha j plus I times of beta j, then e power lambda j of t is nothing but e power alpha j of t e power I beta j of t. When t tends to infinity, if and only if alpha j less than 0. So, what is the remark over here? The proof of this theorem is the general case obtained by using what we call Jordan canonical form of A. Stability of non-homogeneous systems. Many practical situations gives rise to mathematical models of the form that is x dot of t is equal to ax of t plus b, where b is a constant. The stability of such system is also governed by the eigenvalues of the matrix A as follows. So, we will have z of t is equal to x of t minus x bar of t. Then we will have z dot t is nothing but x dot of t minus x bar of t. So, if z of t approaches to 0, then x of t would be approaches to x bar of t. So, therefore, that will conclude the theorem as defined over here. Let us look at further stability theorem for non-homogeneous system of differential equations. An equilibrium solution of 2 is asymptotically stable if and only if all the eigenvalues of A have negative real parts. An equilibrium solution is unstable if at least one eigenvalue has a positive real part. So, stability of a system of differential equations. Like the system of differential equations, there are practical systems which are modeled by system of difference equations of the form x of k plus 1 is equal to ax of k plus b. A well-known mathematical criteria for the asymptotic stability of such system is the following theorem. So, we will have exk plus 1 will be equivalent to axk plus b. Is asymptotically stable if and only if all the eigenvalues of A are inside the unit circle. It is unstable if at least one eigenvalue has magnitude greater than 1. Summarizing, to determine the stability and asymptotic stability of systems modeled by a first order differential equations, all that we need to know is if the eigenvalues of A are the left of plane or inside the unit circle. The explicit knowledge of the eigenvalues is not needed. We'll see second example over here, an European arms race. In the year 1909, 1914, between two European alliances, there is an alliance 1, France and Russia. Alliance 2 is Germany and Austria, that's Hungary. The two alliances went to war against each other. Let's try to explain this historical fact through the notion of this stability. So, when I talk about this stability, there is a first consider the following crude mathematical model of war between two countries. So, I will write this as dx1 by dt is equivalent to k1 x2 minus alpha 1 x1 plus z1, and dx2 by dt will be equivalent to k2 x1 minus alpha 2 x2 plus z2. So, two differential equations which I made over here, where xit is nothing but war potential of the country for I is equal to 1 to 2, that is both the countries, and git is the grievances that country I has against the other for I is equal to 1 to 2. The quantities gi, comma alpha I for I is equal to 1 2 are all positive constants. Alpha I xi denotes the cost of ornament or the country I. This mathematical model is due to Richardson, and we call it as Richardson extrapolation method or Richardson model. Note that this simple model is a realistic in the sense that the rate of change of the war potential of one country depends upon the war potential of the other country, the grievances that one country has against its enemy country, and the cost of the ornaments the country can afford. While the first two factors cause the rate to increase, the last certainly has slowing effect, that is negative sign associated with the term. So, we will have the matrix A is equal to minus alpha 1 k1 k2 minus alpha 2, that is x of t is equal to x1 of t and x2 of t. So, the eigenvalues can be computed by using this expression as we know very well, that is lambda is minus of alpha 1 plus alpha 2 plus or minus square root of alpha 1 minus alpha 2 squared plus 4 times of k1 k2 divided by 2. Thus, the equilibrium solution x of t is asymptotically stable if alpha 1 alpha 2 minus k1 k2 greater than 0, and it becomes unstable when alpha 1, alpha 2 minus k1, k2 less than 0. This is because when alpha 1, alpha 2 minus k1, k2 greater than 0, both the eigenvalues will have negative real parts, and if it is negative, then one eigenvalue will have positive real part. So for the above European arm race, the estimates as we have seen over here, that is alpha 1, alpha 2, k1, k2 were made for realistic assumptions. And if it happens to be alpha 1, alpha 2 is equal to 0.2 and k2 is equal to 0.9, the main assumptions are both the alliances have roughly the same strength. And alpha 1, alpha 2 are same as Great Britain, which is usually taken to be the reciprocal of the lifetime of the British Parliament for a span of particular 5 years. With these values of alpha 1, alpha 2, k1, k2, so we will have alpha 1, alpha 2 minus k1 times of k2 is nothing but alpha 1 square minus k1 square, which would be minus of 0.7700. Thus, the equilibrium is, we proved that it is a unstable. In fact, two eigenvalues are 1.4 and minus of 2.2. So, there are several examples like this. One more example is phenomenon of the resonance. We can see that vibrating structures such as building, bridges and highways sometimes experience a dangerous oscillations, maybe due to resonance or maybe due to seismics or maybe some other property, causing partial or complete destruction of the human being or the structures or even the environment. Some classical and recent events that possibly might have caused by the resonance includes the fall of Tacoma Narrower Bridge in the state of Washington, as we see from the literature which is in the United States. The fall of Broughton Suspension Bridge in England. Similarly, the opening of the Millennium Bridge over the river Thames in London. Also, we have seen such examples over in Gujarat. What we have seen was, there was a, what you call, flying row in the Narmada River, and suddenly it collapsed. So there is a destruction of the human being over there. It happened a year ago, probably. All of you might be knowing. A general model of vibrating structures is a second order differential equations. So we'll write it as m times of x double dot of t plus d times of x dot of t plus k of xt is equal to 0. As we see that m, k, d are respectively known as the mass, stiffness and damping matrices. Substituting this u of t, u times of e power lambda t turns out to be x of t, which we call quadratic eigenvalue problem, which will be written in this following fashion. So, in many practical instances, matrices M, K, D are symmetric, and further we will write M is equal to M transpose greater than 0. K is equal to K transpose greater than 0. Assuming M is non-singular, the quadratic eigenvalue problem reduces to the eigenvalue problem like this. And we can write it as Az is equal to lambda times of Z. Thus, if each of the matrices MKD is of order n, then there are 2n eigenvalues of A, and these 2n eigenvalues are same as those that of P lambda. These eigenvalues are related to the natural frequencies of the structure. The resonance occurs when a frequency of the external force becomes equal or very close to the natural frequency, as explained in the upcoming example. Look at this. I wrote over here x of t will be equivalent to summation k is equal to 1 to 2n alpha k times of zk e power lambda k of t, where lambda k are all distinct values. So we will have the system is excited by an harmonic external force, that is ft is equal to f naught times I power I omega t. Omega is nothing but a frequency. Then a particular solution will become like this for this example. where Yj are left eigenvectors of Pj. This shows that as I omega approaches to value called lambda j, the response of the tile system becomes unbounded and the system produces a resonance which would be a unstable. Similarly, many of the researchers in the literature, they also do have what we call a buckling problem. This is also well-known boundary value problem. Let us consider a thin uniform beam of length L. An axial load P is applied to a beam of one of the ends. We are interested in knowing how when the beam buckles. Let Y denote the vertical displacement of a point of the beam which a distance of x, and there will be a deflection. Suppose both ends of the beam are supplied through what you call y of 0 is equal to y of L is equal to 0, then we will have the equation EI times of d square y by dx square is equal to minus p times of y. And you see from this figure, E is the modulus of elasticity and I is the area moment of inertia of column cross section. And let the interval 0, L be partitioned into n subintervals like this: x0, x1, x2, xn as the point of division. And you know that 0, that is x0 is less than x1 like this, and last one xn is equal to L. That means from this beam we'll have a d square y by dx square. We'll write it as yi plus 1 minus 2ii plus yi minus 1 upon h square. H is the step size in the x direction, and n is the number of divisions which we will make over in the intervals. Substituting this approximation d square y by dx square into the bending moment equation and taking into account the boundary conditions, we will have the following matrix. If you see over here, and this is the main diagonal, this is the subdiagonal. So all these are zeros, so it has become upper triangular matrix, where lambda will have p times of h square ei is the usual meaning. Now each of the lambda determines a load that is called P is equal to lambda ei upon h of square. H is actually the spacing, which is called a critical load. So these critical loads are the ones which are of very practical interest because they determine the possible onset of buckling of the beam. In particular, the smallest value of P is of primary importance, since the bending associated with the large values of P may not be obtained without failure occurring under the action of the lowest critical value of P. So, in today's lecture, what we have learned is how actually the practical applications of differential equations would give rise to us the matrix equations, and how we can find out the direct solutions, how we can find out the iterative solutions, and how the solution becomes a stable solution, and what are the consequences it may prove to be a unstable solutions. Thank you very much for listening to my lecture today. I'll stop over here.